doing here, we want to change the form of the formula. If we work on this form directly, then our solution is not the best one, because we saw some special examples. We can get a better solution. So then, when we do the transformation, we found a special property, factorization. Common factor property. Yeah, let's say common factor property. We noticed common factor property can help us reduce the number of multiplications. How do we take advantage of this common factor property? We apply the factorization technique. Factorization technique here, right? The first time we do experiment, we do it on m equals 2 case. So one factorization here, look at this side. One factorization can help us reduce the number of multiplication from 3 to 2. If we do not do factorization, we need 3 multiplications. After we do one factorization, we reduce it to 2 multiplications. That's what we did last time. Now, let's keep going, but we need to build up our experience. We did one successful, simple example, but it's not enough. We want to do a few more examples to get a better understanding. All right, so let me do another example. N equals 3 case. Yeah. So let's practice. How do we do factorization for n equals 3 case? All right. So this is the cubic polynomial. When n equals 3, cubic polynomial. Now we want to do factorization. Let's repeat the process. Repeat the process we used in the previous example. Idea. How do we do the factorization? Because if you look at here, how many terms do we have? If you look at all the terms here, there are 4 terms. 4 terms, but these 4 terms, they do not have common factor, right? No common factor among these 4 terms. How about if no common factor among the 4 terms, how about we try to find the next best thing? Next best thing, okay? We reduce 4 terms to 3 terms. Can we find a common factor among 3 of the 4 terms? 3 of the 4 terms. There we can do it, right? So that's the second best thing we can do, the factorization. All right, key to the success. Yeah, let's recall. Yeah. The technique, factorization technique, why we can reduce the number of multiplications, the key to the success, this factorization technique. Yeah. All right. When we make our decision on, so here there is a question, how do you apply this technique, right? Yeah. Although you know factorization technique is the key to the success, but there is another question, how do you apply this technique in the right way, right? Yeah, that's not easy. Apply this technique in the right way. So we need to address that problem. Okay, the right way here. Yeah, look at this sentence. Right way. The factorization should cover as many terms as possible. Okay, cover as many as possible. Yeah. First, you try to cover all 4 terms. You failed, right? Yeah, we failed. So now we reduce. Yeah, let's look at how about 3 of the 4 terms? Yeah, that's as many as possible, right? Yeah, that's as many as possible. So the 3 of the 4 terms, we cover the last 3 terms. Yeah. All right. Then we take the common factor X out. All right. After that, what should we do next? Yeah. So we move one step forward. Then, when you look at the remaining part inside the parenthesis, can you see something interesting? The remaining expression inside the parenthesis. Anything interesting based on your experience? Yeah. There are 3 terms inside parenthesis. Can you do another round factorization to cover as many terms as possible? Right? Not all 3 terms. How about two of the 3 terms? Yeah. You can see we can do another round factorization on the last 2 terms inside the parenthesis. Okay? All right. So let's do second round factorization. Yeah? Because the more factorizations you do, the better the improvement, right? Yeah. Every time you apply factorization, you reduce the number of total multiplications. So we want to keep doing factorization until we cannot. Okay? Yeah. We have no room to improve, so we stop. Yeah. All right. So here we do 2 rounds factorization. Yeah. All right. So you can see after 2 rounds factorization, we have this expression. Okay? Yeah. Now, let's look at our improvement. How much is the improvement if we do factorization like this? Yeah. All right. Let's count. How many multiplications do we need from the original form? Okay? Yeah. 1 multiplication, 2 multiplication, 3 multiplication, adding, you get 6 multiplications, right? 1 plus 2 plus 3. All right. Now let's count. How many multiplications do we need in our new form? New form. Okay? All right. X times the whole parenthesis 1 multiplication. All right? Yeah. X times the inner parenthesis another multiplication. Right? X3 times X, third multiplication. So total, you get 3 multiplications. See? See the reduction from 6 to 3 reduction. You can see the previous example, the reduction from 3 to 2, right? Yeah, only 1 reduction, 1 multiplication reduction. But here, 3 multiplication reduction. You can see, because we can do more factorization, right? This example, because we can do 2 rounds factorization, covering more terms. That's the reason our reduction is larger here. Okay? The previous one, only 1 round multiplication, but cover fewer terms. All right? So now you compare. So from these 2 examples, you improve your understanding. Okay? Yeah. Then, our last step, because we cannot work on the special examples again and again, right? Eventually, we need to work on the general case, right? This general case. Yeah. All right. So next step, now we are ready. Yeah. Because now we have plenty of experience. Yeah. Experience from 2 examples. So we are ready to go to the general case. Yeah. But when we go to the general case, keep in mind, we are going to, this is our strategy. Yeah. We implement the strategy when we go to the general case. What's the strategy? Here, what we are going to do, we apply certain method, but this is a general strategy. What's the third method here? Third method here refers to factorization. Yeah. Because later, when we work on different problems, we need to change the certain method to some other different method. Yeah. In this example here, it's the factorization. We apply the factorization technique as much as possible. When we go to the general case, that's our strategy. Okay, all right. So this method, in algorithm theory, so there is a special name for this method. We call it greedy algorithm. Greedy algorithm. Okay? So you apply some special method as much as you can. Yeah, so that's some, using the word greedy word to describe that idea. So we call it greedy algorithm. So next, we will apply this greedy algorithm to do the factorization. Yeah. All right. Yeah. Idea, push this method to the general case. Yeah. Here, the strategy. Yeah. Do factorization as much as we can. Yeah. So that's the, the underlying approach, the greedy algorithm approach. All right, so greedy idea here. Yeah. So let me explain this greedy algorithms. So what's the greedy algorithm? Apply some property as much as we can at each step. Yeah. At each step, you apply some greedy strategy. Yeah. Greedy algorithm, each step, you need to define your greedy strategy. Yeah. For different questions, your greedy strategy is different. Yeah. So here, let me explain this greedy strategy. What is our greedy strategy here? Yeah. All right. Greedy strategy, this is greedy strategy, right? Do factorization as much as we can. That's the greedy strategy. Covering as many terms as we can. That's the greedy strategy, right? Yeah. Yeah. All right. But here, when you apply the greedy strategy, you need to understand in two different views. One is the local view, another is the global view. Yeah. Here, each step, when we apply our greedy strategy, each step, it's a local. It's a local. It's a portion of the whole solution, right? It's only one step. Only one step you apply greedy strategy. So your greedy strategy is applied on a portion of the solution. So we call it, it's a local approach. Local, not global. Global, you should apply your strategy covering the whole solution, not a portion of the solution. Yeah. So here, it's a local approach, not global approach. Yeah. Why we apply greedy strategy locally, not globally? Yeah. The reason is very simple. Yeah. Apply the greedy strategy locally. It's easy. Apply your greedy strategy globally, too hard. We cannot do it. Okay? Nobody can do it. Okay? Globally, covering all the steps. Nobody knows how to do it. But only one step, then it's easy, right? Yeah, everybody can do it. That's the reason. So why greedy algorithm is so useful? Because easy to apply. Yeah. All right. But because it's easy to apply, when we make a local decision, it is optimal, right? Yeah. Local decision, we do the best we can. That's optimal. But if you look at it globally, it may not be optimal. So each local decision, you get an optimal result, but you put them together, then you look at it, your solution globally, actually, many times you won't get a global optimal solution. Yeah. So that's the main property of the greedy algorithm. Globally, sometimes you get an optimal solution, sometimes you do not get an optimal solution. Yeah. Yeah. All right? Yeah. So we will see. Yeah, because when we understand more and more about the greedy algorithm, you will see. You will get a better understanding of this greedy algorithm. All right. It may not be optimal globally because it could be the reason is very hard to make a global optimal solution, right? Yeah. Because you need to consider all the possible factors globally. That's too hard. That's too hard. Yeah. Yeah. So that's the, main property of this greedy algorithm. Yeah. All right. So now, let us apply the greedy strategy. General form. Yeah. Round by round. The first round covering as many terms as possible. All these. So we skip the first term. Yeah. All the remaining terms, they share a common factor, so we can do one round factorization. Yeah. All right. So, but because we have our old experience, can we use our previous example? Yeah. Use the form in this example to help us, guide us to find the new factorization form. Yeah, that's this one. Okay, round by round. Yeah, keep doing. Yeah, every time you do one round factorization, then you get into the inner parenthesis, another round, inner parenthesis, another round, until this last round. Okay, yeah. In the last round, the innermost pair of parentheses, you cannot do any factorization, right? No more factorization. Then you stop. Yeah. So this special way, we call it Horner's rule. If you calculate your polynomial in this, we call it Horner's rule. Okay? Not use the, brute force way. This is the brute force way. This is, if you calculate polynomial in this way, the Horner's rule method. Yeah. Now you can understand our programming project number 1 better, because our first method, brute force. Okay? Brute force, you calculate. Yeah. Then our second, I need to talk about it later. This Horner's rule is our third method. Use this structure to calculate your polynomial. Yeah. Second, next slide, we have another method to calculate. Yeah. All right? Yeah. Then, after that, we need to count number of multiplications. When we do Horner's rule method, how many multiplications do you need? Can you see how many multiplications do we need if we do Horner's rule? Do the counting. Do the counting here. Any idea? This is a general polynomial, degree n. N is not fixed. Right, n is not fixed. So your answer should be in terms of n. in terms of n. It's another concrete number. Okay? Yeah. In terms of n.
Is it just n?
Yes, correct. Yeah, just n. Yeah. Can you explain a little bit? Why you see it's n?
If you look at P3 of x and count it, it follows that pattern.
All right.
You know that
Yeah, okay.
these three
Yeah.
have three multiplications on that one.
All right, yeah. So yeah, because in your mind, you know the way, yeah, because based on your understanding, right? Based on your understanding. Yeah. But for other students, now I want to explain in a way you can apply, without any fuzzy thing. Yeah. So, yeah. All right. So if you can apply a method clearly, remember we learned one special counting method in our first lecture. We call it counting by reference method. Still remember? Counting by second lecture, not first lecture. Second lecture. Counting by reference. Yeah. Here, let's do the counting by reference. Yeah. Because here, there is a technical problem. Look at dot, dot, dot here. Okay? Dot, dot, dot here. That means we have some difficulty in keeping track of the data, right? Dot, 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 you may get lost, right? Yeah. When you do the counting, going through dot, 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 you skip certain number of terms, but how to keep track of those terms. Yeah. Now, let's find appropriate reference objects. Yeah. All right. Each multiplication we associate with a certain simple, easy, straightforward object. All right, so this is the first multiplication, right? We want to associate with this subscript 1. How about that? First multiplication, we do 1-to-1 correspondence with this object subscript 1. Second multiplication, this here, we associate with the next subscript, A2, the subscript in this A2 coefficient 2. How about that? Okay. The next one, each one we associate with its, right adjacent, the subscript of its right adjacent coefficient number. How about that? That kind of 1-to-1 correspondence. Okay? All right. The last multiplication, this is the last multiplication. Last multiplication associated with the, its own subscript, right? Yeah, AN, right here. Okay? All right. Then when you do the counting, when you count the number multiplication, is it the same as you count the number of subscripts? Right? And your subscripts, they are consecutive integers from 1 through n. Right? Yeah. Counting integers, consecutive integers from 1 through n. That's easy. That's n, right? Yeah. So you try to use this method. So we learn in our second lecture, counting by reference. Then you won't get lost. Okay? You can keep track of your data. Because here, although we have dot, 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 but we have confidence because we know these consecutive integers, we can count them easily. Nobody will get lost, right? Counting consecutive integers covering certain range, nobody will get lost. Okay? Yeah. All right. Yeah. Try to use this method. All right. Yeah. Right? Yeah. Yeah. All right. Then look at the improvement. So we get an answer. What is the improvement? Next, B.4, visualize performance improvement. Is it a big improvement or small improvement? We want to see that. So B.4. All right. So let's look at that. we see the difference in formula. First, because there are two formulas we can compare. Yeah. Before we do the improvement, the formula is this many multiplications. Yeah. After we do the factorization, so we get this many multiplications. Yeah. Yeah. We know it's an improvement, yeah, significant improvement. Yeah. But the question is, do you have some visual understanding on the improvement? Yeah. Here we only see the formula difference, right? But in your mind, can you visualize how large is the improvement? Yeah. Here we want to do that. Yeah. Visualization on the improvement, yeah, to impress ourselves. Yeah. Let me use two examples to help you visualize the improvement. All right. Impact of multiplication reduction. Yeah. How big is the multiplication reduction in this example? All right. All right. Yeah. Because if you look at the formula, too abstract. Okay? Two math formulas. You know they are different, but you have no visual images in your mind. Yeah. All right? So we want to build that image. Yeah. It is better try a couple of concrete examples. Let's try two examples here. Okay? Two special examples for two different n special values. Yeah. The first n value we want to try, n equals 1,000. 1,000, a polynomial with degree 1,000, right? Yeah, it's a pretty big polynomial. 1,000 plus 1 terms. Yeah? Number of terms, 1,000 plus 1 terms. All right. Then let's plug in into the first formula, second formula, and do comparison. When we plug in n equals 1,000 into this first formula, yeah, yeah, we get approximately 500,000. Yeah, yeah. Here I do not use the precise number. Yeah, precise number could be messy, right? So I try to use approximate number here. Okay, 500,000. Yeah, yeah. Many times we do approximation. Yeah, so that's good enough. Yeah. All right. So here, what you can see in our first example, the difference is 500,000 versus 1,000. How much is the difference between these two numbers? Is it big? Yeah. If you take the ratio, yeah, here if we take the ratio, 500 to 1 ratio. Okay, 500 to 1 ratio. Okay, yeah. If you apply the brute force method, you need a certain amount of time, but now you switch to Horner's rule, the execution time you need 500th of the original time, right? 500th of original time. 1 over 500. That much. How much is that? 500th. Is it about 0.2%? Is it? Yeah, if we use the percentage, is it the 0.2% of the original time? If the first method brute force we use T0, okay, then we switch to Horner's rule, second method. The time you need 0.2% of the T0. Is it big improvement? Huge improvement, big improvement? Yeah, that's our first example. Second example, yeah. Let me use another much larger n number here. This time n equals 1 million. Because right now we are in big data era, right? Big data era. So sometimes you need to do data processing on your data size, very large data size. Here, 1 million. That's also possible. Yeah. You may encounter 1 million data items when you do data processing. Right? All right, so if n is 1 million, you plug in the first formula, this time approximation. Yeah. N is 1 million. Yeah. But when you plug in this formula, 1 million, you get this number. What is this number? Yeah. Can you call it quickly? Yeah. 500 billion, not trillion, right? Billion, yeah, not trillion. Okay, yeah, 500 billion. Then let's take ratio. Take ratio to see what's the ratio. 500,000 to 1 ratio. Yeah. This big, the difference huge, like this. Okay, all right. Then let me do another concrete way to let you see the difference. Yeah, concrete way to let you see the difference. Yeah, here, although you know this ratio is so big, yeah, but if we use our real world experience to understand this big ratio number, how big is the difference? Yeah. So let's use this way. This one, let us use 1 second. Yeah. So if you apply Horner's rule using the, in this second method, yeah, let's say this one corresponds to 1 second. Okay, 1 second. Yeah. Then the same polynomial, you use the brute force, the first method, brute force, you need 500,000 seconds. Right? 500,000 to 1 ratio. 500,000 seconds, how long is that time? 500,000 seconds, how long is that? Okay? We can do conversion, convert to hours, days, right? So after I do conversion, approximately 5.8 days. That difference. Same formula, 2 different methods. One, you only need 1 second. The other one, you need 5.8 days. Look at the difference. Okay? Yeah. Yeah. So you can see the efficiency of the algorithm is so big, so important. Why efficiency of the algorithm is extremely important? From this example, you can see. Yeah. If you do not use the Horner's rule, you calculate. You calculate a huge polynomial with this many terms. Yeah. Imagine, so you are doing, so you are an engineer, so you calculate, some satellite, related data with this many terms. Okay. Yeah. But if you only know the brute force method, if you do not know the Horner's rule, you only know brute force method. Yeah. Many people, 90-something% of the people, they only know the brute force method. Okay. Then you write a program, calculate that 1 million term polynomial. After you hit enter, you need to wait 5.8 days to get the answer. 5.8 days to get the answer. All right? Then, after you learn this class, because you know Horner's rule, so you can do much better using this Horner's rule. So you change your program, you write the code using the Horner's rule implementation. Then suddenly, the same huge polynomial, but you only need 1 second to get the answer. Yeah. This example, our first project, we try to feel about this huge difference. But the data I give you, I cannot let you wait 5.8 days to get the answer, right? Yeah. We cannot afford it. Yeah. Too expensive. Yeah. So I reduce that time, 5.8 days, I reduce to 2 to 5 seconds. Yeah. The first method, I let you control your execution time to 2 to 5 seconds. Okay? Yeah. That's a lot of time, right? Yeah. When we run it on our computers, you need to wait 2 through 5 seconds because some computer are very powerful, some not very powerful. So I let you control your execution time between 2 and 5 seconds. Yeah, when you hit enter, you need to wait some time, right? You can see, wait quite some time. Yeah, but then the other one, because in milliseconds. Yeah. So if we use the Horner's rule, the same polynomial, you calculate in milliseconds. Yeah. Then let you feel the difference. That's our first project. Okay, all right. Yeah. Yeah. So we finished this topic. Any question? Yeah. Yeah. But we have our second method you need to do in your first project. So next, let's learn our second method. Yeah. All right. So, yeah. B.5, repeated squaring technique. Yeah. Repeated squaring technique. Yeah. So another interesting method. Yeah. Sometimes it can do better than Horner's rule, but most of the time, Horner's rule is better. Yeah. Most of the time, Horner's rule is better. Yeah. Yeah. But I also want you to compare 3 methods. Yeah. All right. But when we start, we work on monomial. Only one term, monomial. Yeah. We did some example before, monomial. Yeah. But here I want to discuss the method we used before systematically. Yeah. All right. Yeah. Given arbitrary monomial, yeah. Not a special one. Yeah, we did a special one before, but here we want to do a general monomial. Yeah. Question: how to find an efficient way to calculate this value? Yeah. All right. Yeah. 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 Here I'll give you the reference in the textbook. Yeah. Section 6.5. Yeah. All right. Then, what do we have so far? Yeah. We learned something. Yeah. We learned Horner's rule. Yeah. Yeah. For monomial, if you apply Horner's rule, it does not improve much. Okay? If you apply Horner's rule on the special monomial, no improvement. No improvement. Okay? Yeah. Yeah. Because Horner's rule, the reason you can do much better in Horner's rule, you apply it on the general formula, yeah. Not the special monomial. Yeah. Special monomial, Horner's rule cannot improve the overall efficiency. Yeah. All right. Yeah. All right. So, yeah. But for the general case, we are very satisfied. Yeah. About the efficiency of the Horner's rule. Yeah. All right. But for special case, yeah, then you will see we're not satisfied. So if we apply Horner's rule, yeah, we won't be satisfied. Yeah. Why? Yeah. Because let me show you. Yeah. We did this x to the 4th before. Yeah. We do the square operations twice. Yeah. Yeah. 2 multiplications. Square operations twice. Yeah. The first time, first square, x times x, it's a square operation. Okay? Yeah. The second time, x squared times x squared, the second square operation. Yeah. So then we just need 2 multiplications. Yeah. All right. So here we call it repeated squaring technique. Yeah. So this technique we call it repeated squaring technique. Yeah. All right. Now, let me use the general case to show you the power of this technique. Yeah. How powerful it is. Yeah. All right. But this time we consider the exponent number n should be a power of 2. Yeah. Then we can keep doing the square operation, yeah, power of 2 number. Yeah. All right. So let's do experiments. Yeah. Yeah. All right. First column, k column, yeah, number. Second, monomial x to the n, but the n equals power of 2. Yeah. Yeah. The third column, we count the number of multiplications we need. Yeah. All right. When k equals 1, yeah, k equals 1, x to the 2 to the first, right? Yeah, because n equals 2 to the k, 2 to the first. Okay? So it's 2 squared, x squared. You calculate x squared, so you need 1 multiplication. Yeah. When k equals 2, you do x to the 4th, yeah, because 2 squared. 4 equals 2 squared. So you need to do x to the 4th. So you do square operation twice. Yeah. Square operation twice. So you need 2 multiplications. When k equals 3, yeah, 2 to the 3rd, x to the 2 to the 3rd, x to the 8th. 8th. Yeah. So you need to do another square operation on x to the 4th. Another square operation. Yeah. So you need 3 multiplications. Okay? All right. The general case, k, yeah, here, for the general case k, yeah, you need to calculate x to the 2 to the kth. Yeah. So you need to do multiplication k times. K times. Okay? Yeah. So that's the result you can enjoy from repeated squaring technique. Repeated squaring technique. Yeah. So when you calculate monomial, if you use this way, much faster than you use direct multiplication. Yeah? If you do not use this way, you do multiplication, use a for loop to do multiplication, right? Yeah. That way, much slower than this way. Yeah. All right. Let me use another example to show you the big difference. All right. Let's look at k equals 10. When k equals 10, if we use two methods, yeah. One is we run a for loop to calculate monomial. Second, repeated squaring. Okay. All right. K equals 10, then the monomial becomes x to the power of 2, 2 to the 10th. 2 to the 10th equals this 1024. Yeah. So when we calculate x to the 1024, you need 10 multiplications, right? 10 multiplications. Yeah. Yeah. What is it? Yeah, too bright, right? Yeah. I mean, we can, a little dark. Oh, not this one. This one. Yeah, this one. All right. Yeah. You can see, if you use a for loop to calculate this monomial directly, how many multiplications do you need? 1023. Not 24, 23. 1023. Yeah. But if you use repeated squaring, 10 multiplications. How big is the difference? 1023 versus 10. Big difference, right? Yeah. Yeah. And this repeated squaring, yeah, is related. One of our quiz questions, remember? Quiz questions. Yeah. Quiz question, as I remember, number 9. Okay? Quiz question number 9. If you answer quiz question number 9, study repeated squaring and this example here. Okay? Yeah. Use the understanding here to help you answer Q9 of quiz 1. Okay? Yeah. All right. Yeah. Q10, yeah. We have another topic. Yeah. Another topic. Okay. So that's why I ask you delay, but I noticed a few students already submitted. Yeah. Submitted quiz 1. Yeah. Yeah. So last 2 questions you need to delay. Yeah. After this class, you can understand, answer better. Yeah. All right. Yeah. Essence of the method. Yeah. Here, why this method can improve efficiency so much. The essence of this method, yeah. Reuse the resource as much as we can to save operations. Resource. Yeah. Here, so our view. So how do we understand the resource here? Yeah. The intermediate calculation results, we treat the intermediate calculation results the resource. Yeah. For example, the first time after you do first multiplication, you have x squared. This x squared we treat it as a resource. Okay? Because it's useful. Why we call it a resource? Because this number is useful when we calculate x to the 4th. Something useful, we treat it as a resource. Okay? So it's our computing resource. It's useful when we do computation. Yeah. So this, the main idea here is when we try to improve our computation, a very important idea is try to reuse your resource, reuse your computation resource as much as you can. The more you can reuse, the better your efficiency. That's the general idea. Okay? Yeah. All right. So here, yeah. The first time we see this idea. Yeah. All right. Then next. Yeah. But in the previous slide, we consider n is power of 2, but the general case n is not a power of 2, right? Yeah. The general case n is not power of 2. Yeah. So we want to see when n is not power of 2, can we still apply the repeated squaring technique? Yeah. All right, so here, let me use a simple example to explain. Yeah. When n is not power of 2, yeah. We use the idea, reuse the resource idea. Yeah. Try to reuse the resource. Yeah. Intermediate calculation results. That's our computation resource. Yeah. All right. Here, I select n equals 217. Yeah. Not power of 2. Okay. Yeah. But we can represent it using power of 2 numbers, sum of power of 2, right? We can represent it as the sum of power of 2 numbers. Okay? If you can do that, then we can still apply repeated squaring technique. Yeah. All right. Yeah. What is the largest power of 2 under n? Largest power of 2 under n. Okay? Yeah. The first question. Yeah. 128. Yeah. Equals 2 to the 7th. Yeah. Because if you use 2 to the 8th, that's 256. It is greater than 217. So we cannot use that. So we have to accept this 2 to the 7th. No. All right. The fastest way to get x to the 128. Yeah. So now, this time, we want to do preparation. Yeah. So when we calculate, so our destination, so our goal, we want to calculate x to the 217. But to do that, we need to do some preparation. Now, the preparation, calculate x to the 128 for the preparation step. Yeah. How to get this number? X to the 128. Yeah. It's a power of 2. 128 is a power of 2. We can keep doing the square operations to get this number. Okay? Yeah. All right. So you can see we need to do 7 multiplications to get this number. 7 multiplications. Yeah. Because the reason is 2 to the 7. Okay? The number of multiplication you need is this exponent number, 7. Okay? Yeah. All right. Reuse the resource. Yeah. Now we use this idea. How do we reuse the resource? Okay? Yeah. Let us put all the useful intermediate results. Let's collect all the useful intermediate results in the pool. Yeah? In the pool, in our preparation, we need to, get that pool ready. Yeah. So we need this, these are the intermediate. Actually, x itself also useful. Yeah, we can put it in the pool. Yeah. All right. Yeah, so all these numbers, we may need to use some of them. Yeah, in our preparation step here. Yeah. We know these intermediate results could be useful. So we save them. Yeah, for the next round computation. Yeah. First round, preparation step. This is our first round, preparation step. Then the second round, we need to work on our goal expression. Yeah. All right. Yeah. We do decomposition. Yeah. In order to use the known numbers. Yeah. So here, all these numbers, they are known numbers. In order to use these known numbers to help us get our destination number, we need to do decomposition. Okay? Decomposition on the n number 217. Yeah. All right. The first round decomposition, we write 217 as the largest power of 2. That's 128 plus 89. Yeah. But 89, we need to split another time, 89, using power of 2, 64. Yeah, the largest possible power of 2, 64. That is less than 89. And plus some number, 25. 25, we can use 16 plus 8 plus 1. Now you can see we represent 217 as a sum of power of 2. Okay, sum of power of 2. Yeah. After we get this decomposition expression, yeah, next we can write our destination expression as product of these, our resource numbers, right? The product, okay? Yeah, the first one, x to the 128th. Yeah. Second number, x to the 64th. Yeah. Third, x to the 16th. Yeah. Next, x to the 8th, and x. Yeah. How many multiplications when you do here? 1, 2, 3, 4, right? Yeah. Yeah. After you get your resource numbers, you still need 4 more multiplications. Yeah. But to get all your resource numbers, you need 7 multiplications. Okay? In your preparation step, you need 7 multiplications. But after the preparation, you need 4 more. Okay? So the total number of multiplications you need here, 7 plus 4 equals 11. Here you can see when you apply repeated squaring operation to calculate this example, x to the 217, you need 11 multiplications. How about that? It's a big improvement, right? Yeah. Big improvement. Okay? Yeah? Yeah. So it's another interesting method. Yeah. This is our second method in our programming project number 1. Okay? 1, 2, 3. 3 methods. Yeah. So after this class, you can start working on the programming project number 1. Okay? Yeah. So because you understand everything. Yeah. All the knowledge needed. Yeah. So we covered everything. Yeah. Yeah. All right. General process. Yeah. Let's look at the general process. Yeah. Summary here. Find the largest k such that 2 to the k less than n. Yeah. Preparation. Yeah. Because you need to build that resource pool, right? Yeah, you need to, the first round, yeah, build up that resource pool. Okay? Yeah. All right. You need a k multiplications to build your resource pool. Yeah. All right. And you know, 2 to the k plus 1 is strictly greater than n. Yeah. Because in that way you can say you get the largest power of 2 less than or equal to n. Yeah. Yeah. Otherwise, you can increase that k number. Yeah. If this inequality is not true, you can increase that k number. Okay? Yeah. All right. So next, based on this inequality, you can get this inequality. And less than equal to 2 to the k plus 1 minus 1. Okay. Yeah. Why? It's very simple. Yeah, to understand this why, because here your inequality is strictly greater than. Yeah. You compare 2 integers. Yeah. Left-hand side, 2 to the k plus 1 is an integer. Right-hand side, and another integer. These 2 integers, the first integer is strictly greater than second integer, then you can say the first integer is at least 1 more than the second integer, right? Yeah, at least 1 more, okay? Yeah. So if you reduce the first integer by 1, then it should be greater or equal to second integer, right? Yeah. It has some room, okay? So you just reduce the larger integer by 1. By 1. Okay? Yeah. There is a chance it equals the first integer. Oh, yeah. Good. Okay. Yeah. So we're near the break time. Yeah. All right? Yeah. So let me finish this slide. Yeah. So we can take a break. Yeah. All right. All right. So n less than equal to 2 to the k plus 1 minus 1. All right. Because with this expression, you can see any number, any n in this range can be represented as our resource numbers. Here, I want to make this argument. Yeah. All right. Yeah. Because if we use our geometric series. This is a geometric series, right? Yeah. Geometric series. When we apply our the formula, we do the summation of geometric series. We have this formula, right? Yeah. Yeah. Because if you calculate summation of this geometric series, yeah, your answer is this one. Okay? Yeah. This one. Now you see, yeah, this number is the largest in this range, right? So we want to represent the n number in this range. Yeah. So the largest number in this range, it's a sum of all our power of 2 numbers, right? In our resource pool. Yeah. the sum of all the power of 2 numbers corresponding to the terms we calculated in our resource pool. Yeah. So we can get it. Yeah. In any number in this range, we can select some of the resource numbers to make it. Yeah. So here I want to make this argument. Yeah. So that means after you prepare your resource pool, that you can represent any number in the given range. Yeah. You won't miss anyone. You can always represent any number in the range. Okay? Yeah. All right. Yeah. How to form x to the n? Yeah. So now, yeah, form. Select elements from the set, from your resource pool. Okay? Select. Yeah. 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 Select based on the decomposition. Decomposition. Okay? But this decomposition closely related to the binary representation of n, right? Here. Yeah. Yeah, because some of them could recognize what we are doing here. Actually, it's a binary representation. Yeah. Corresponding to your binary representation. Yeah. Yeah. 1, 0, 1, 0, 0, you skip that power of 2. If you see 1, you need to select the corresponding power of 2. 0, you skip it. 1, 0, 1, 0. So the binary representation will tell you the decomposition information. Okay? Yeah. Yeah. All right. Oh, let's take a break. Yeah. All right. So, yeah. All right.